In this video, we will talk about the simplified finite difference method. Uh, I have already created a few videos on that where I discussed the simplified finite difference method. In this video, we will solve the paper by Khan and Pop, which is a good paper, published in 2010. It is an old paper, but a very good paper to learn new things. So as you follow the videos, then you can see that we already solved this paper by BVP4C and it was running fine. I hope you already ran that code which I shared with you in description. So we start simplified finite difference method for this paper, which is a simple paper. Then we will apply simplified finite difference method to the other problems, which will be a bit complex. Equation 1 is continuity equation. Equation 2 is momentum equation. Equation 3 is energy equation, and equation 4 is nanoparticle concentration equation. As I mentioned earlier in my previous video, when I was solving these equations with BVP4C, I mentioned that these are not the boundary layer equation since we did not apply the boundary layer assumptions on these equations. So you can apply boundary layer assumption. Recently, this is a very common practice to write the equation in boundary layer form. So you have to do that yourself. Then we have similarity transformation. We apply similarity variable. We introduce similarity variable over here and apply that to the PDEs. Then we get equation A, B, and C. Equation A is a third order differential equation. Equation B is energy equation, and there is a nanoparticle concentration equation. Let me just emphasize one thing over here. I just typed all these equation over here. You have to download the paper, this paper, and see yourself all the equations so that there can be a typo mistake. I know I have checked it, but it can happen that we have a typing error. So you have to see the paper yourself. This is just a side note. Now we have a boundary condition. This is given in that paper. Now, this is a very recent work that we introduced in the paper, simplified finite difference method. This is not a finite difference method. It is a different scheme, but we want to introduce a new scheme just for fun, or maybe just to introduce some new numerical method to see the accuracy and anything. So you must follow that and spend some time on that. I will share all the details over here. In the beginning, probably you will not understand it since we introduce it at that time. Then it took us some time to understand the logic behind the simplified finite difference method. As you follow the previous videos, I already discussed from which book that we actually um, took that idea and implemented, just modified it so that we can get the simplified finite difference method. We are not calling this method as a finite difference method since it is not a finite difference method. So one option was we call it the modified finite difference method. but it doesn't look good, so we call it simplified finite difference method, since it becomes a simple finite difference scheme. That's what the name is all about. So you have to follow this series if you want to apply this simplified finite difference method for your problem. My MS students are working on this method as well. They are also taking the different problems, and we are applying this method to those fluid models. You can also do that. I will share the code with you in the description. Probably it will take you 2 to 3 days if you work uh, uh, thoroughly on that, then you can understand. So this was all about the simplified finite difference method, and I don't want to waste much time on explaining what is all this about. So the first thing you have to do in simplified finite difference method is to reduce the order of your momentum equation. Momentum equation A, which is this one, A has third order ODE. It is a third order ODE, and simplified finite difference method is only applicable to third order ODE, second order ODE. So we need to reduce the order. So what we do, we defined a new variable, f dash is equal to capital F. Then we we take another derivative, f dash is equal to f double dash, and f double dash will be equal to small f dash. When you put these values in the momentum equation, you get this equation, which is equal to chi1. You put f double dash with coefficient is equal to 1 on the left hand side, keep that on the left hand side, and put all the values on the keep all the values on the right hand side, which is equal to chi1. Then we have an, we take a derivative of this chi1 with respect to f dash, capital F dash, and take a minus. There is a reason which I already explained in my previous video. I will not going to explain that again. If you ask in the comment, it will be, I mean, it will just waste the time. So you have to watch that video, which I already shared with you. So an is already f, small f. Bn, you take a partial derivative of chi1 with respect to capital F and take a negative sign, then you get minus 2f. Then we have dn, capital Dn is equal to chi1 plus a capital An capital F dash plus Bn capital F. That's it. That is a theoretical part. Remember that when you are doing this on the page, then you should put the value of chi1 into dn, capital Dn, right? Now we move to the energy equation. We do the same. We keep theta double dash. Since theta energy equation is second order, we don't need to reduce the order of this ODE. We keep this as it is. Keep theta double dash on the left hand side. Then we have all the values on the right hand side, and we call that chi2. And theta double dash is chi2. We take up and we do the same. A capital A n will be equal to minus partial chi2 by partial theta dash. You get the right hand side. Then b n, if you take a derivative of chi2, remember that this is chi2, and take a derivative of chi2 with respect to theta, you can see that there is no theta involved in chi2, so the derivative will be 0. And we do the same dn chi2 plus a n theta dash plus b n n theta, and we do the same that chi2, you put the value of chi2 over here. That was all about energy equation. The same will be done for concentration equation. First, you keep phi double dash on the left hand side with coefficient 1. Remember that the coefficient should be 1. And keep all the other values on the right hand side and call it chi3. Then again, use capital A with triple N and take a derivative of chi3 with respect to phi dash and take a negative sign, then b triple n is equal to 0 and so on. That was all about the theoretical calculation. If you do not understand, then try to do it again and again and you will be comfortable with it. Then here is the MATLAB code. I just explained this to you. There are actually two codes for this, two functions for this code. There is one which is a main code, and there is another code which is a function file, which actually deals with tridiagonal matrix algorithm or LU decomposition. You define parameters. Then we have left domain a is equal to 0, b is equal to 4, and then we have step size. Then we have domain coordinates. It should be coordinates. Then this is the boundary, but here we are just calling it f0 is equal to 1, fn is equal to 0, theta 0 is equal to 1, and so on. Here you can see why there is a capital F, since if you see in the boundary condition, you can see that f dash is equal to 1, and we are calling that f dash is equal to capital F. So that capital F will be equal to 1, and for all you will, in all the papers, mostly f0 is equal to 1. When there is a change, we will change it in future. Number of iterations, then we initialize the capital F, theta, F, phi. Since capital F is a new variable, theta is the temperature, small f for momentum, phi is for 0. All we just initialize it. There is nothing new about that. We also initialize a n, b n, dn. Then we go to the for loop. This will remain the same for you. If you have chi, for example, microorganism equation, then you add one value over here. Small capital AN will be equal to F, and it should start from 2 to n. Why 2 to n? Since at 1 there is a boundary. And remember that AN, this AN is equal to small f, and this is the same small f has been used in the code. But since we are applying finite difference, so f should start from 2 to capital N. Bn is minus 2 to f2n, which is the same as we calculated earlier, and theoretically we did it, and you have to do for your own problem. An is f, bn is minus 2 capital F, so we call it capital F. We continue with this dn. Dn is chi1 and some other values you can see from the theory. You can pause the video, go back and see what was dn. Dn was chi1 and chi1 was this term, so on. So you pause the video, spend some time on it, and this is dn. This is the function file that we will use for a solution of momentum equation. And we do the same for energy equation as well. Capital AN, BN, DN, and so on. This remains the same. Then we have, when we have a linear ODE, linear ODE means that we have linear boundary conditions, then you write like this. F1 will be equal to 0. This is the boundary, and this is actually your F dash. You remember that what we have put it over here, F dash is equal to small f. This one, small f dash, is equal to capital F. What we do, we apply forward difference on f dash and find out the value of f. Since we already calculated capital F, we already calculated this second order capital F equation, and we need to find the original solution, which is small f. So we calculate that again by using the forward difference. This is the solution, capital F, but we don't require that. We require small f, which is a momentum equation. Here I used forward difference. Take a page and apply forward difference on theoretically on f, small f dash is equal to capital F. You will get this equation. We do the same again. Now the solution has been computed. Now we do it for the energy equation. This is for energy equation. And again, this is second, the function file has been used again. I will show you this second order linear ODE file. Then we have this boundary is over here and boundary is over here, and you are getting theta AP from this file, this function file. Now the solution has been computed from here. We don't need this thing like we have it for momentum, since we do not put it, we have not put it f dash or theta dash is equal to some theta. It was only required, this f is only required when we have to reduce the order. So we calculated the solution over here. You don't need to change this further. You only need to put a and bn. Again, for phi, this is an, and remember that when you will see it, this is the, whenever there is a derivative in an or bn somewhere, you have to keep it as sometime forward difference. Here we will use forward difference. Again, this is dn. Here you can see that there was this phi dash, and we used the forward difference over here. Now that we got the solution, that's it. I just run the code. I just run it. You will see the F2D, which is skin friction coefficient over here. This is skin friction coefficient. This is theta dash. This is phi dash 0. Okay, you got the solution. You got the solution from where? You got the solution from by using these formulas. Since your skin friction coefficient is, let me just write it over here, it is F double dash 0. You need this one, something like skin friction defined like this. Since you are calling small f dash is equal to capital F, this will be equal to F dash 0. That's what I used over here. I used F1 minus F2, something like that. And again, theta dash 0 and so on. You got the solution from simplified finite difference method. Okay, let me just show you. Let me just show you the second function file. This was this function file. Since this is a simple problem and we do not need to change this. This is the function file. All the calculation are here. All the calculation are here. I will share the link of one of my paper where we have introduced this thing. Okay, so I will share with you in the description. You just search it and read that paper. So this video was a bit longer, and my suggestion is to take some time, since it also took us some time to understand or develop this simplified finite difference method. So I'll share the code with you. Thank you for watching.